All right, folks, these are the answers to problem number 1. We have a 3 ohm bulb and an 8 ohm bulb in pure parallel. So we have one complete circuit going through the 8 ohm bulb and the 9-volt battery, and one complete circuit going through the 3 ohm bulb and the 9-volt battery. And you can see from the different colors that you can go through the 8 or the 3, but not both, right? That's why it's called parallel. So you have 2 independent lazy river rides. Okay. Question A is find the total resistance. That's not a great word because total makes you think add the 8 plus 3. So a better way to say this would be find the effective resistance. But anyway, don't get confused by the word total. So 1 over R tot equals 1 over 3 plus 1 over 8. And so 1 over R tot equals 0.4583 repeating. You might be tempted to think that that is your final answer, but that's the inverse of the answer. So R tot, you're going to take the inverse of both sides of your equal sign, oops, not squared, I'm on autopilot, to the -1. And that means R tot is 2.18 ohms. And that should make sense. Continue to check your work. That if you have a 3-minute, a checkout person or TS agent who takes 3 minutes, and then you hire someone who takes 8 minutes, it's going to make it better, but not amazingly better because 8 is worse than 3. So the 3-minute goes down to 2.18 minutes. Okay, so makes sense it's less than 3, but not like cut in half. Okay, so that is our total resistance. What that means, super quickly, is the total current, which we'll, I assume, get to in a minute, is, so what the battery thinks is that it has a single 2.18 ohm bulb. That's what it's providing current to. Okay, question B says find the current in the 3 ohm bulb. So let's do this in orange. The 3 ohm bulb, you can see, thinks it had, the 8 ohm bulb is irrelevant. The 3 ohm bulb has a complete circuit. So the current through the 3 is the voltage over the resistance, which is 9 volts over 3 ohms. It has 3 amps going through it. Find the current through the 8. And notice we're using R individual here, not R total, because you have 2 independent loops. Whereas if they were in series, you'd have to use R total because you couldn't go through the 3 without also going through the 8. So 9 volts over 8 ohms, which is 1.125 amps. Okay, then D is find the current through the battery. So there's 2 ways to do this. They would both get full credit. I total is going to be I3 plus I8. Because if you go back and look at the diagram, that's what's going through the battery. The purple electrons and the orange electrons. So that's 3 amps plus 1.125 amps, or 4.125 amps. Okay, that should make sense, right? Both loops go through the battery, so that's the total current. The other way to do that, to check your work, is that the current through the battery, which you might want to call I tot, is V over R tot, or R effective. And the voltage is 9 volts, and you're like, why the heck did we find the total resistance and we're not going to use it? That's how you could use the total resistance, and you would, not surprisingly, get 4.125 amps. Okay, so nice way to check your work. All right, E, calculate the wattage of the 3 ohm bulb and then the 8 ohm bulb. this should be old hat to y'all. This is no different in that it's the rate at which that light bulb is converting electron energy to light. And so the more electrons come in, the faster they're coming in, the more light you're going to get, right? Because each electron is bringing a certain amount of energy, and the more energy the light bulb takes away, the more bright it's going to be. But we are going to use in the individual because we just want to care. We only care about how bright that bulb is. Okay, so you've got the reason we're doing combination circuits second is because you got to be really careful. There's multiple currents. Which one I'm going to use? So you might want to say I individual. It's clearly only the electrons going through that light bulb can create light. So I'm using the orange current squared times 3 or 27 watts. And then the power of the 8 is, make sure you use that current, because for the last 2 weeks, you've always been using the same current. So don't go on autopilot and go, oh, I already know the current. Go make sure you know the right current. And again, the individual resistance, and that is 10.1 watts. So if you, just a quick aside, if the 8 and the 3 were wired in in series, they'd have the same current. So the 8 would be brighter because the same current squared, whoever has more resistance is going to be brighter. But here you can see that the 3 ohm bulb is brighter because it has more current and the current is squared. So even though it has less resistance, it has proportionally the same amount of more current, and that's going to be squared. Okay, so you can always check your work with the formula, but that's the logic behind it. Okay, so we found the 2 wattages. And then the last question is, find the energy used by the entire circuit in 4 minutes. All right, so energy is power times time. So we need to do the whole circuit. So the power is going to be 37.1 watts, but I'm going to rewrite a watt as a joule per second, which will remind you, oh, the time needs to be in seconds. So I have 4 times 60 seconds, and that comes out to be 8,904 joules. Again, a joule is a tiny, tiny unit. It is about 13 to 18 cents for 3.6 million joules. No, 1,000 joules, kilowatt. So anyway, it's a tiny unit for energy. Okay, awesome. That was question 1. Hope that went well. Question 2. Julia wires a 17 ohm bulb to a 20 volt battery. So we have 1 complete loop for that system and some other apparently unknown light bulb hooked up to the same voltage. Calculate the current in the bulb. So that green loop, completely independent. So we don't care what else is going on. I equals V over R. 20 volts over 17 ohms is 1.18 amps. Calculate the wattage of the bulb. .18 squared times 17 is 23.5 watts. And then she's like, oh, that is not bright enough for whatever she's doing. She wants the total power to be 40. So then we got to figure out what other resistance we should plug in. So again, this is a little bit more of a think about everything that's going on. We want 40 total. So let's figure out how much this bulb has to be. So 40 minus 23.5 we need this bulb to be 16.5 watts. Okay. And then, on my PDF key, I'm using a formula that I really don't like people to use because it's just, you got to be really careful with it. So I'm going to try to do it another way. Okay. What resistance should the second bulb have? Okay. So we know that the power of the second bulb is I squared R. We want that to be 16.5. Don't use the 1.18. That green current is different from the orange current. What is the orange current? The orange current is 20 over R. And we're going to square it. And then we're going to multiply it by R. Right, so it's a little bit more complicated, but there is only one unknown here. Okay, so 16.5 equals 400 over R squared times R. And we can cancel one R. And then I would suggest we cross multiply. So we have 16.5 times R equals 400. And then we divide both sides by 16.5. And we get R equals 24.2 ohms. Okay, so a multi-step problem and a little bit of algebra. But you all have been doing great at the, you've done that on some worksheets and FET labs and tests. So awesome. So we know what the resistance is. Let's put that up here, 24.2 ohms. Calculate the total resistance of this circuit. So again, do not get confused by total. Total means effective. So 1 over R tote is 1 over R1 plus 1 over R2. So 1 over, what do we got? 1 over 17 plus 1 over 24.2. So 1 over R tote equals 0.100. That is not your answer. That's the inverse of your answer. So we're going to take the inverse of both of these to get R tote. So you can just raise this to the -1. Your calculator might also have an inverse option. So you get R tote is 9.985 or 9.99 ohms. Okay, so again, check your work. That's about, let's just say 10 ohms just for logic. So you have one checkout clerk that's 24 minutes and another checkout clerk that's 17 minutes. So those are roughly, to 1 sig fig, that's almost 20 minutes and 20 minutes. So clearly if you're twice as good as 20 minutes, that's about 10 minutes, which is what we got. So yay, that makes sense. Okay, and then last question is calculate the current in the battery. So again, there's 2 ways to do it. You could add both currents up, which we didn't find the current in the second one, the second bulb. So let's say I tote equals V over R tote. And we have a 20 volt battery and effectively 9.99 ohms. So that is, I'm going to divide by all of the sig figs because it's already in my calculator. 2.002 perfect amps. Okay, but you could have we knew that the green current was 1.18. You could have found the orange current by doing 20 over 24.2 and adding both of those. Okay, question 3 is just a little different, just to mix things up, but it's more of a guess and check than a, not really guess, it's just a keep doing this until something happens kind of problem. Okay, so Veronica's camping. She's got a 12 volt power supply, and then she's got all these different appliances, and apparently this is the order in which she finds them important. She likes her coffee, she wants fresh breath, or to not get cavities, then she wants a waffle, that's, and And then she wants some music, and then maybe she wants some pancakes, or eggs with the griddle. Okay. So she's going to keep using stuff until the fuse blows. Okay. So calculate the current that each device will have when hooked up to the battery. So this is pretty straightforward. You remember each appliance thinks it has the voltage all to itself. So you're going to have 12 volts over 15 ohms, which is 0.8 of an amps. And then I'm not going to keep writing the formula. 12 over 7 is 1.71 amps. And then 12 over 12, shocker, 1 amp. 12 over 6, double shocker, 2 amps. And 12 over 9 is 1.3 repeating amps. Okay, so we have all of our currents and it that's what each of these appliances would we say draw or pull. That's the current that would be in each of these separately, but the current through this is the sum of all of those individual currents, because they all have to go through the battery. Okay, so we did A. If she plugs each device in one at a time, which device will cause the 4 amp fuse to break? So unlike the demo we did in class, there's a 4 amp fuse here, and it's going to have the orange current going through it, and then the orange and the purple, and then the orange, purple, and the red. And when that gets to 4 amps, it will break and nothing will work. Okay, so this is what I was saying before. We're just going to, there's no easy way to do it. We're just going to keep adding currents until we get over 4. Okay, so she plugs in the coffee maker and she has 0.8 amps. That's less than 4. Then we're going to add the next appliance. She's up to 2.51. Then we're going to add the next appliance. Oh, we're getting close. 3.51. Then we're going to add 2. And we're at 5.51 amps. That is greater than 4, so the radio is going to break the fuse. Okay, so again, that's not really a very standard problem because it's not really testing logic. It's more just of like a practical question. And just the understanding that you keep adding, like in your house, the more stuff you plug in, you just keep adding the current. Okay, and then I see and see that I also use the formula that I really don't want you using, so assuming she could plug in only one device, which would require the least power from the battery, calculate this power. So least power, think about power. The battery's fixed at 12 volts. So power, the energy the battery has to supply, or the rate at which it's got to supply energy, is I times V, and V is fixed at 12. So if we want the least power, that means we want the least current, which means we want the most resistance. So let's look and see what we have here. Okay, 15 ohms is the most resistance. So if we want to really conserve that battery, then we're going to plug in just the coffee maker. And we want the power. And again, there is I'll just quickly tell you why this formula only works once we do more complicated circuits. The voltage that an appliance sees, we've seen this before in series, they're sharing the voltage. The voltage that this appliance gets isn't always all 12 volts. So that's why I don't like that. I just don't like that formula. So we want, this is just better, I think, because it's saying, I know this is related to converting the electron energy to, in this case, what is it, a coffee maker, to brewing the coffee, heat to brew the coffee. And I already found the current going through that is 0.8 amps. So power equals 0.8 amps squared times 15 ohms, which is 9.6 watts. Okay, so if this question were on a test, again, I would hope that you would go through the logic of which one. Clearly it's going to be one of the extremes, either the biggest resistance or the smallest resistance. And you could always check both to see which one is least, but again, I hope that you think deeply about why that makes sense. That, oh, to get the least, to use up the least energy, I need the fewest current, right? Because each electron that goes through each coulomb that goes through is committed to getting 12 joules. So if I want to not use up power, I better have a low current, because then I'm trick-or-treating more slowly. I'm running out the candy more slowly. Okay, awesome. We're at 20 minutes. Thanks for hanging in there. Let's do question 4. So she has a 4.7 ohm light bulb and a 3.5 ohm light bulb, and she knows she gets one measurement for whatever goofy reason. She measures this, and she knows the current there. And what does she want to know? She wants to know the voltage of the battery. So again, I'm drawing the orange loop just so I don't forget, but do you see how like the purple loop was its own independent thing? So that if you ignore this 3.5 ohm, whatever it is, you got a single loop circuit. You got the resistance, you got the current, and you want to know the voltage. Okay, so I equals V over R. We know that I is 2.7. We don't know the V. R is 4.7. So multiply both sides by 4.7. And you get that the voltage is 12.7 volts. Yay. All right, now calculate the current in the 3.5 ohm bulb. So that orange current is V over R because you have an independent loop. And now we know the voltage. And so that is 3.63 amps. Okay, so we know that 3.63 amps. Check. Calculate the total resistance. This is a lot of these other formulas you've been using a lot. This is the one that I hope you are starting to feel good about, but this is the one that you should practice because this is what's new. So 1 over R total equals 1 over 4.7 plus 1 divided by 3.5. So 1 over R equals about a half. And that's not your answer. You got to take both sides to the -1. This turns into R, and that turns into 2.01 ohms. Because the inverse of a half is it's about a half, so the inverse is going to be 2. Okay, that is the total resistance in a circuit, and then almost done with the worksheet. That was C. D is find the current in the battery. 2 ways to do it. You could take 3.63 plus 2.7. Equals 6.33 amps. Or you could say the current is the voltage over the total resistance. Sorry, I'm at the corner of my drawing. Okay, so that is 12.7 volts over 2.01 ohms. So you can see, 12 divided by 2 would be 6, but it's a little bit more than 12. So we get a little bit more than 6. 6.33 amps. Let me just check. Okay, so that is the Pure Parallel worksheet. Thank you for listening, and I will see you in class.